Welcome to Mrs. Z's Chemistry. In this video, we'll complete Chapter 7 by learning how to draw resonance structures. First, let's draw SO2. We have 6 valence electrons for sulfur and then 6 more for each oxygen. So we have a total of 18 valence electrons. So we're going to put sulfur in the middle, and we're going to just start by single bonding the oxygens. We have placed 4 electrons so far. 6, 8, 10, 12, 14, 16, 18. So we have a total of 18 valence electrons. Sulfur does not have an octet the way it's written, so we're going to take a lone pair from oxygen and place a double bond here. Now, Lewis structures most often are symmetrical. The molecules like to be symmetrical, so often the bonds are going to be the same if we've got the same atom attached to the central atom. So because sulfur can have an expanded octet, any element that is in period 3 on the periodic table or lower, sulfur is in period 3, they can have an expanded octet or more than just 8 electrons. So even though sulfur has 8 shared electrons right now, we can actually take a lone pair from the other oxygen and make another double bond. So we've got 2 double bonds on sulfur with also a lone pair. That's 10 shared electrons on sulfur. Oxygen each has an octet. Now, this is not a problem to draw it this way because sulfur can have the expanded octet. But if we were to have a element in the middle that can't have an expanded octet, but we have a similar situation here, this might we might run into a problem. So this is why we need to learn how to draw resonance structures. And we're going to look at this example. NO2-. This is the nitrite ion. Nitrogen has 5 valence electrons. There are 2 oxygens, each with 6 valence electrons. Plus, then we have 1 for the charge. So we have 18 valence electrons again. We're going to put nitrogen in the middle. And we're going to just do our little skeletal structure here with the oxygens on either end. And we have placed a total of 4 electrons. So now we can 6, 8, 10, 12, 14, 16, and 18. We have placed all of our electrons. We cannot place any more. Oxygen does not have an octet, and so we will actually erase a lone pair and place a double bond between nitrogen and oxygen. The right-handed oxygen has an octet, the nitrogen now has an octet, and the left-handed oxygen also has an octet. However, we cannot place another double bond on nitrogen because then nitrogen would have an expanded octet. Nitrogen is in period 2, row 2 on the periodic table, and it cannot have an expanded octet. So, the issue with this, though, why we can't just leave it like this, is that experimental evidence tells us that the 2 oxygens bonded to nitrogen actually have the same bond. So we don't have 1 double and 1 single. We have 2 bonds that are the same. So how do we draw this with Lewis structures, knowing we can't have an expanded octet? Well, we need to actually draw this molecule a second time, showing the double bond on the other side. First, let's complete this structure by putting brackets around it with a -1, showing the -1 charge on the outside. And we're going to draw it again, but we're going to put the double bond on the left-handed oxygen. The single bonded oxygen gets 3 lone pairs, the double bonded oxygen gets 2 lone pairs, and the nitrogen gets 2 lone pairs. Complete the structure with brackets and the negative charge, and we need to put a double arrow in the middle, right here. This is what is meant or called resonance, when we have to draw the structure twice to show a more accurate model of the molecule. So here's the structure shown. This is the same answer here for NO2-. We have the structure shown in a trigonal planar or bent molecular shape. The Lewis structure doesn't have to show the shape, but this is a more accurate showing of what the geometry of this molecule looks like. All right, so resonance. This is if you have 2 or more Lewis structures with the same arrangement of atoms that can be written for a molecule or ion, and then the actual distribution of the electrons is an average of that, shown by the various Lewis structures, 2 or sometimes even 3 or 4. So looking at this again, this molecule doesn't have 1 single bond and 1 double bond. It actually has 2 bonds that are roughly 1.5 bonds. They're the same type of bond. And the reason this is important is because single and double bonds and triple bonds are actually all different. Single bonds are longer than double bonds, and double bonds are longer than triple bonds. So triple bonds are the shortest. However, triple bonds are the strongest bond. The double bond is less strong, and the single bond is the weakest. So if we were to say that, in fact, this molecule did have one double and one single, that would mean that this oxygen would be closer to nitrogen than the single bonded oxygen, because double bonds are shorter. It would also mean that the double bonded oxygen is more strongly bound to nitrogen than the single bonded oxygen. But that's not true. Experimental observations shows that the two oxygens are the same distance from nitrogen and equally bound to nitrogen with the same strength of bond. Lewis structures, then the model for Lewis structures kind of falls apart here, which is why we have to draw it twice to show the 1.5 rather than one single and one double. So let's do another example. Pause to see if you can work this out. Nitrogen has 5 valence electrons. There are 3 oxygens, plus 1 more for the charge. We have a total of 24 valence electrons. Our skeletal structure would look something like this. We've placed 6 electrons so far. 8, 10, 12, 14, 16, 18, 20, 22, 24. Nitrogen does not have an octet, and we have no more electrons to place around it. So we need to take a lone pair off of oxygen and make a double bond with that oxygen. So this is where you know that you have to draw Lewis resonance structures. And because we're just going to randomly or arbitrarily choose an oxygen. Well, which one do we choose? Do we choose the right-handed one, the left-handed one, the bottom one? Or if you were to draw the structure with the oxygen on top instead of the bottom, like which oxygen are you going to choose? This tells you you're going to do all 3 of them. You just do one of them first. Let's close this in with brackets and put a -1 charge. Now let's go ahead and draw this 2 more times with that double bond in the different locations. Because I have technology, I'm going to just oops, can I copy that? Copy and paste this and then adjust it. So let's put the double bond on the other side. Let's also draw the lone pair here and take the lone pair off of there. The double bonded oxygen needs to have the 2 lone pairs, and the single bonded oxygens get 3 lone pairs. Let's do it one more time. Can I paste it again? Let's see here. All right, so now we're going to put the double bonded oxygen on bottom. The double bonded oxygen has the 2 lone pairs again, and the single bond has the 3 lone pairs. We complete our resonance structures by drawing the double arrows between each structure. Now remember that the Lewis structures do not need to show the shape. However, the shape is a trigonal planar shape. You have 3 attached atoms to nitrogen. They are going to spread out as far away from as possible from each other and not be in a T shape the way I drew them. Though this is perfectly acceptable for Lewis structures because Lewis structures are not meant to show the shape. But often when you look it up, you'll see the Lewis structure showing the shape, and it's a little bit easier to visualize what's actually happening with the molecule. So remember also that the molecule that has resonance structures never exists as either or any of the structures drawn. So none of these structures actually exist with 1 double and 2 singles. You have to imagine that these structures are superimposed on top of one another, and that the actual molecule that does exist is an average of the resonance structure. So here we would have more of a 1 1/3 bond. It would be a little bit shorter than a single bond, but longer than a double bond. And it would also be a little bit stronger than a single bond, but weaker than a double. So it's somewhere in between. Go ahead and pause to see if you can work this one out. And here is the answer for the carbonate ion. We have 3 resonance structures. There are 3 places or 3 oxygens bonded to carbon. So each one is going to take a turn, so to speak, with a double bond, even though there actually is no double bonds and no single bonds. These are, again, 1 1/3 bonds.